Chapter 9. Optics. Exercises. Exercise pages 1 to 185. Exercises Q1. Page 184. Choose the correct option. As per the recent understanding, light consists of 1. Rays 2. Waves 3. Corpuscles 4. Photons obeying the rules of waves. Solution: photons obeying the rules of waves. Exercises Q1. Page 184. Choose the correct option. Consider the optically denser lenses P, Q, R, and S drawn below. According to the Cartesian sign convention, which of these have a positive focal length? 1. Only P2. Only P and Q3. Only P and R4. Only Q and S. Solution: only P and Q. Exercises Q1. Page 184. Choose the correct option. Two plane mirrors are inclined at angle of 40 degrees between them. Number of images seen of a tiny object kept between them is 1. Only 8, 2. Only 9, 3. 8, or 9. 4, 9, or 10. Solution: two plane mirrors are inclined at angle of 40 degrees between them. Number of images seen of a tiny object kept between them is 8 or 9. Exercises Q1. IV page 184. Choose the correct option. A concave mirror of curvature 40 cm, used for shaving purposes, produces image of double size as that of the object. Object distance must be 1. 10 cm only 2. 20 cm only 3. 30 cm only 4. 10 cm or 30 cm. Solution: 10 cm or 30 cm. Exercises Q1. B page 184. Choose the correct option. Which of the following aberrations will not occur for spherical mirrors? 1. Chromatic aberration. 2. Coma. 3. Distortion. 4. Spherical aberration. Solution: chromatic aberration. Exercises Q1. B page 184. Choose the correct option. There are different fish, monkeys, and water of the habitable planet of the star Proxima b. A fish swimming underwater feels that there is a monkey at 2.5 meters on the top of a tree. The same monkey feels that the fish is 1.6 meters below the water surface. Interestingly, height of the tree and the depth at which the fish is swimming are exactly same. Refractive index of that water must be. Solution: 5/4. Exercises Q1. B page 184. Choose the correct option. Consider the following phenomena. Applications: P. Mirage, Q. Rainbow, R. Optical fiber, and S. Glittering of a diamond. Total internal reflection is involved in 1. Only R and S2. Only R3. Only P, R and S4. All the 4. Solution: only R and S. Exercises Q1. B page 184. Choose the correct option. A student uses spectacles of number -2 for seeing distant objects. Commonly used lenses for his spectacles are 1. Biconcave. 2. Double concave. 3. Concavo-convex. 4. Convexo-concave. Solution: a student uses spectacles of number -2 for seeing distant objects. Commonly used lenses for his spectacles are biconcave. Exercises Q1. X page 185. Choose the correct option. A spherical marble, of refractive index 1.5 and curvature 1.5 cm, contains a tiny air bubble at its center. Where will it appear when seen from outside? Solution: at the center. Exercises Q1. X page 185. Choose the correct option. Select the wrong statement. 1. Smaller angle of prism is recommended for greater angular dispersion. 2. Right-angled isosceles glass prism is commonly used for total internal reflection. 3. Angle of deviation is practically constant for thin prisms. 4. For emergent rays to be possible from the second refracting surface, certain minimum angle of incidence is necessary from the first surface. Solution: smaller angle of prism is recommended for greater angular dispersion. Exercises Q1. Sheet page 185. Choose the correct option. Angles of deviation for extreme colors are given for different prisms. Select the one having maximum dispersive power of its material. 1. 7 degrees, 10 degrees 2. 8 degrees, 11 degrees 3. 12 degrees, 16 degrees 4. 10 degrees, 14 degrees. Solution 7 degrees, 10 degrees exercises Q1. See page 185. Choose the correct option. Which of the following is not involved in formation of a rainbow? 1. Refraction 2. Angular dispersion 3. Angular deviation 4. Total internal reflection. Solution total internal reflection exercises Q1. See page 185. Choose the correct option. Consider the following statements regarding a simple microscope. P. It allows us to keep the object within the least distance of distant vision. Q. Image appears to be biggest if the object is at the focus. R. It is simply a convex lens. 1. Only P is correct. 2. Only P and Q are correct. 3. Only Q and R are correct. 4. Only P and R are correct. Solution. Only P and R are correct exercises Q2. Page 185. Answer the following question. As per recent development, what is the nature of light? Wave optics and particle nature of light are used to explain which phenomena of light respectively. Solution I. As per recent development, it is now an established fact that light possesses dual nature. Light consists of energy carrier photons. These photons follow the rules of electromagnetic waves. E. Wave optics explains the phenomena of light such as interference, diffraction, polarization, Doppler effect, etc. E. Particle nature of light can be used to explain phenomena like photoelectric effect, emission of spectral lines, Compton effect, etc. Exercise Q2. Page 185. Which phenomena can be satisfactorily explained using ray optics? Solution. Ray optics or geometrical optics. Ray optics can be used for understanding phenomena like reflection, refraction, double refraction, total internal reflection, etc. Exercises Q2. Page 185. Answer the following question. State the assumptions on which ray optics is based. Solution. Ray optics is based on the following fundamental laws. I. Light travels in a straight line in a homogeneous and isotropic medium. E. Two or more rays can intersect at a point without affecting their paths beyond that point. E. Laws of reflection. A. Reflected ray lies in the plane formed by the incident ray and the normal drawn at the point of incidence, and the two rays are on either side of the normal. B. Angles of incidence and reflection are equal, I equals R. IV. Laws of refraction. A. Refracted ray lies in the plane formed by the incident ray and the normal drawn at the point of incidence, and the two rays are on either side of the normal. B. Angle of incidence θ1 and angle of refraction θ2 are related by Snell's law, given by n1 sin θ1 equals n2 sin θ2, where n1, n2 equals refractive indices of medium 1 and medium 2 respectively. Exercises Q2. Page 1. Answer the following question. What is focal power of a spherical mirror or a lens? What may be the reason for using P equals 1, F as its expression? Solution I. Converging or diverging the ability of a lens or of a mirror is defined as its focal power. E. This implies, the more the power of any spherical mirror or lens, the more is its ability to converge or diverge the light that passes through it. E. In the case of a convex lens or concave mirror, the more the convergence, the shorter is the focal length as shown in the figure. IV. Similarly, in the case of a concave lens or convex mirror, the more the divergence, the shorter is the focal length. B. This explains that the focal power of any spherical lens or mirror is inversely proportional to the focal length. B. Hence, the expression of focal power is given by the formula, P equals 1 F. Exercises Q2. IV page 185. At which positions of the objects do spherical mirrors produce diminished image? Solution. Amongst the two types of spherical mirrors, convex mirror always produces a diminished image at all positions of the object. Concave mirror produces diminished image when object is placed a. beyond radius of curvature, i.e., u greater than 2fb. At infinity, i.e., u equals infinity. Exercises Q2. B page 185. At which positions of the objects do spherical mirrors produce a magnified image? Solution. Amongst the two types of spherical mirrors, the convex mirror always produces a diminished image at all positions of the object. Concave mirror produces magnified image when the object is placed a. between center of curvature and focus, i.e., 2f greater than u greater than fb. Between focus and pole of the mirror, i.e., u less than f. Exercises Q2. B page 185. At which positions of the objects do spherical mirrors produce a magnified image? Solution. Amongst the two types of spherical mirrors, the convex mirror always produces a diminished image at all positions of the object. Concave mirror produces magnified image when the object is placed a. between center of curvature and focus, i.e., 2f greater than u greater than fb. Between focus and pole of the mirror, i.e., u less than f. Exercises Q2. B page 185. Answer the following question. Define absolute refractive index and relative refractive index. Explain in brief with an illustration for each. Solution I. Absolute refractive index of a medium is defined as the ratio of the speed of light in a vacuum to that in the given medium. E. A stick or pencil kept obliquely in a glass containing water appears broken as its part in water appears to be raised. E. As the speed of light is different in two media, the rays of light coming from water undergo refraction at the boundary separating the two media. IV. Consider the speed of light to be v in water and c in air. Speed of light in air approximately equals speed of light in vacuum, therefore refractive index of water. Exercises Q2. B page 185. Answer the following question. Explain mirage as an illustration of refraction. Solution I. On a hot, clear, sunny day, along a level road, there appears a pond of water ahead of the road. However, if we physically reach the spot, there is nothing but the dry road and water pond again appears some distance ahead. This illusion is called mirage. E. Mirage results from the refraction of light through a non-uniform medium. E. On a hot day, the air in contact with the road is hottest, and as we go up, it gets gradually cooler. The refractive index of air thus decreases with height. Hot air tends to be less optically dense than cooler air, which results into a non-uniform medium. IV. Light travels in a straight line through a uniform medium but refracts when traveling through a non-uniform medium. V. Thus, the ray of light coming from the top of an object get refracted while traveling downwards into less optically dense air and become more and more horizontal as shown in figure B. As it almost touches the road, it bends, refracts upward. Then onwards, upward bending continues due to denser air. B. As a result, for an observer, it appears to be coming from below, thereby giving an illusion of reflection from an imaginary water surface. Exercises Q2. X page 185. Answer the following question. Under what conditions are total internal reflection possible? Explain it with a suitable example. Solution. Conditions for total internal reflection. I. The light ray must travel from denser medium to rarer medium. E. The angle of incidence in the denser medium must be greater than critical angle for the given pair of media. Total internal reflection in optical fiber. I. Consider an optical fiber made up of the core of refractive index N1 and cladding of refractive index N2 such that N1 greater than N2. E. When a ray of light is incident from a core denser medium, the refracted ray is bent away from the normal. E. At a particular angle of incidence IC in the denser medium, the corresponding angle of refraction in the rarer medium is 90 degrees. IV. For angles of incidence greater than IC, the angle of refraction becomes larger than 90 degrees and the ray does not enter into the rarer medium at all but is reflected totally into the denser medium as shown in the figure. Exercises Q2. X page 185. Answer the following question. Define the critical angle of incidence and obtain an expression for it. Solution. The critical angle for a pair of refracting media can be defined as that angle of incidence in the denser medium for which the angle of refraction in the rarer medium is 90 degrees. Let n be the relative refractive index of a denser medium with respect to the rarer. Exercises Q2. See page 185. Answer the following question. Describe the construction and working of an optical fiber. Solution. Construction. I. An optical fiber consists of an extremely thin, transparent, and flexible core surrounded by an optically rarer flexible cover called cladding. E. For protection, the whole system is coated by a buffer and a jacket E. The entire thickness of the fiber is less than half an m. IV. Many such fibers can be packed together in an outer cover. Construction of optical fiber working. I. Working of optical fiber is based on the principle of total internal reflection. E. An optical signal, a ray of light entering the core suffers multiple total internal reflections before emerging out after several kilometers. E. The optical signal travels with the highest possible speed in the material. IV. The emerged optical signal has an extremely low loss in signal strength. Working of optical fiber. Exercises Q2. See page 185. Answer the following question. What are the advantages of optical fiber communication over electronic communication? Solution advantages. I. Broad bandwidth frequency range for TV signals. A single optical fiber can carry over 90,000 independent signals channels. E. Immune to EM interference. Optical fiber being electrically nonconductive, does not pick up nearby EM signals. E. Low attenuation loss. Loss being lower than 0.2 decibels per kilometer, a single long cable can be used for several kilometers. IV. Electrical insulator. Optical fibers being electrical insulators, ground loops of metal wires or lightning do not cause any harm. B. Theft prevention. Optical fibers do not use copper or other expensive material which are prone to be robbed. B. Security of information. Internal damage is most unlikely to occur, keeping the information secure. Exercises Q2. See page 185. Answer the following question. Why is prism binoculars preferred over traditional binoculars? Describe its working in brief. Solution I. Traditional binoculars use only two cylinders. Distance between the two cylinders can't be greater than that between the two eyes. This creates a limitation of the field of view. E. A prism binocular has two right-angled glass prisms that apply the principle of total internal reflection. E. The incident light rays are reflected internally twice, giving the viewer a wider field of view. For this reason, prism binoculars are preferred over traditional binoculars. Working. Prism binoculars I. The prism binoculars consist of four isosceles, right-angled prisms of a material having a critical angle less than 45 degrees. E. The prism binoculars have a wider input range compared to traditional binoculars. E. The light rays incident on the prism binoculars first get total internally reflected by the isosceles, right-angled prisms 1 and 4. IV. These reflected rays undergo another total internal reflection by prisms 2 and 3 to form the final image. Exercises Q2. See page 185. Answer the following question. A spherical surface separates two transparent media. Derive an expression that relates object and image distances with the radius of curvature for a point object. Clearly state the assumptions, if any. Solution I. Consider a spherical surface YPY, of radius curvature r, separating two transparent media of refractive indices n1 and n2 respectively with n1 less than n2. E. P is the pole and x-vex is the principal axis. A point object O is at a distance u from the pole, in the medium of refractive index n1. E. In order to minimize spherical aberration, we consider two paraxial rays. IV. The ray op along the principal axis travels undeviated along with px. Another ray OA strikes the surface at A. Refraction at a single refracting surface V. As n1 less than n2, the ray deviates towards the normal cant travels along with as, and a real image of point object O is formed at I. B. Let alpha, beta and y be the angles subtended by incident ray, normal and refracted ray with the principal axis. Therefore I equals alpha plus beta, and r equals beta minus gamma b. As the rays are paraxial, all the angles can be considered to be very small, i.e., sin I approximately equals I and sin r approximately equals r. Assumptions. To derive an expression that relates object and image distances with the radius of curvature for a point object, the two rays considered are assumed to be paraxial, thus making the angles subtended by incident ray, normal and refracted ray with the principal axis very small. Exercises Q2. She page 186. Answer the following question. Derive Lens-Maker's equation. Why is it called so? Under which conditions focal length f and radii of curvature r are numerically equal for a lens? Solution I. Consider a lens of radii of curvature r1 and r2 kept in a medium such that the refractive index of the material of the lens with respect to the medium is denoted as n. E. Assuming the lens to be thin, P is the common pole for both the surfaces. O is a point object on the principal axis at a distance u from P. E. The refracting surface facing the object is considered as the first refracting surface with radii r1. IV. In the absence of the second refracting surface, the paraxial ray OA deviates towards normal and would intersect the axis at I1. Pi1 equals version 1 is the image distance for intermediate image I1. Exercises Q3. I page 186. Answer the following question in detail. What are the different types of dispersions of light? Why do they occur? Solution I. There are two types of dispersions. A. Angular dispersion. B. Lateral dispersion. E. The refractive index of material depends on the frequency of incident light. Hence, for different colors, the refractive index of the material is different. E. For an obliquely incident ray, the angles of refraction are different for each color and they separate as they travel along different directions, resulting in angular dispersion. IV. When a polychromatic beam of light is obliquely incident upon a plane parallel transparent slab, emergent beam consists of all component colors separated out. B. In this case, these colors are parallel to each other and are also parallel to their initial direction, resulting in lateral dispersion. Exercises Q3. E page 186. Answer the following question in detail. Define angular dispersion for a prism. Solution. If a polychromatic beam is an incident upon a prism, the emergent beam consists of all the individual colors angularly separated. This phenomenon is known as angular dispersion for a prism. Exercises Q3. E page 186. Answer the following question in detail. Obtain angular dispersion expression for a thin prism. Relate it with the refractive indices of the material of the prism for corresponding colors. Solution I. For any two component colors, angular dispersion is given by delta 21 equals delta 2 minus delta 1. E. For white light, we consider two extreme colors viz. red and violet. Therefore delta Vr equals delta V minus delta R. E. For thin prism, delta equals a n minus 1, therefore delta 21 equals delta 2 minus delta 1. equals a n2 minus 1 minus a n1 minus 1 equals a n2 minus n1, where n1 and n2 are refractive indices for the two colors. IV. For white light, delta VR equals delta V minus delta R. Equals a nb minus 1 minus a nr minus 1 equals a nb minus nr. Exercises Q3. E page 186. Answer the following question in detail. Explain and define the dispersive power of transparent material. Obtain its expressions in terms of angles of deviation and refractive indices. Solution I. The ability of an optical material to disperse constituent colors is its dispersive power. E. It is measured for any two colors as the ratio of angular dispersion to the mean deviation for those two colors. Thus, for the extreme colors of white light, dispersive power is given by Exercises Q3. IVI page 186. Answer the following question in detail. State the conditions under which a rainbow can be seen. Solution: a rainbow can be observed when there is a light shower with a relatively large raindrop occurring during morning or evening time with enough sunlight around. Exercises Q3. IVE page 186. Answer the following question in detail. Explain the formation of a primary rainbow. For which angular range with the horizontal is it visible? Solution: 1. A ray AB incident from sun white light strikes the upper portion of a water drop at an incident angle I. 2. On entering into the water, it deviates and disperses into constituent colors. The figure shows the extreme colors, violet and red. Formation of primary rainbow. 3. Refracted rays VB and BR strike the opposite inner surface of water drop and suffer internal reflection. 4. These reflected rays finally emerge from B and R and can be seen by an observer on the ground. 5. For the observer, they appear to be coming from the opposite side of the sun. 6. Minimum deviation rays of red and violet color are inclined to the ground level at theta r equals 42.8 degrees approximately equals 43 degrees and theta b equals 40.8 approximately equals 41 degrees respectively. As a result, in the rainbow, the red is above and violet is below. Exercises Q3. IVE page 186. Answer the following question in detail. Explain the formation of a secondary rainbow. For which angular range with the horizontal is it visible? Solution: 1. A ray AB incident from sun white light strikes the lower portion of a water drop at an incident angle I. 2. On entering into the water, it deviates and disperses into constituent colors. The figure shows the extreme colors, violet and red. Formation of secondary rainbow. 3. Refracted rays BB and BR finally emerge the drop from B and R after suffering two internal reflections and can be seen by an observer on the ground. 4. Minimum deviation rays of red and violet color are inclined to the ground level at theta r approximately equals 51 degrees and theta b approximately equals 53 degrees respectively. As a result, in the rainbow, the violet is above and red is below. Exercises Q3. IVIV page 186. Answer the following question in detail. Is it possible to see primary and secondary rainbow simultaneously? Under what conditions? Solution: yes, it is possible to see primary and secondary rainbows simultaneously. This can occur when the centers of both the rainbows coincide. Exercises Q3. VI page 186. Answer the following question in detail. Explain chromatic aberration for spherical lenses. State a method to minimize or eliminate it. Solution: 1. Lenses are prepared by using a transparent material medium having a different refractive index for different colors. Hence angular dispersion is present. 2. If the lens is thick, this will result in notably different foci corresponding to each color for a polychromatic beam, like a white light. This defect is called chromatic aberration. 3. As violet light has maximum deviation, it is focused closest to the pole. A. Chromatic aberration in convex lens. B. Chromatic aberration in concave lens reducing, eliminating chromatic aberration. I. Eliminating chromatic aberrations for all colors is impossible. Hence, it is minimized by eliminating aberrations for extreme colors. E. This is achieved by using either a convex and a concave lens in contact or two thin convex lenses with proper separation. Such a combination is called achromatic combination. Exercises Q3. BE, page 186. Answer the following question in detail. What is achromatism? Derive a condition to achieve achromatism for a lens combination. State the conditions for it to be converging. Solution. 1. To eliminate chromatic aberrations for extreme colors from a lens, either a convex and a concave lens in contact or two thin convex lenses with proper separation are used. 2. This combination is called an achromatic combination. The process of using this combination is termed as achromatism of a lens. 3. Let omega-1 and omega-2 be the dispersive powers of materials of the two-component lenses used in contact for an achromatic combination. 4. Let B, R and Y denote the focal lengths for violet, red and yellow colors respectively. Exercises Q3. B, page 186. Answer the following question in detail. Describe spherical aberration for spherical lenses. What are the different ways to minimize or eliminate it? Solution I. All the formulae used for image formation by lenses are based on some assumptions. However, in reality, these assumptions are not always true. E. A single point focus in case of lenses is possible only for small aperture spherical lenses and for paraxial rays. E. The rays coming from a distant object farther from the principal axis no longer remain parallel to the axis. Thus, the focus gradually shifts towards the pole. IV. This defect arises due to the spherical shape of the refracting surface, hence known as spherical aberration. It results in a blurred image with unclear boundaries. Spherical aberration in convex lens. Spherical aberration in concave lens B. As shown in the figure, the rays near the edge of the lens converge at focal point FM. Whereas, the rays near the principal axis converge at point FP. The distance between FM and FP is measured as the longitudinal spherical aberration. B. In absence of this aberration, a single point image can be obtained on a screen. In the presence of spherical aberration, the image is always a circle. B. At a particular location of the screen, across AB in the figure, the diameter of this circle is minimum. This is called the circle of least confusion. The radius of this circle is transverse spherical aberration. Methods to eliminate reduce spherical aberration in lenses. 1. The cheapest method to reduce spherical aberration is to use a planiconvex or planiconcave lens with a curved side facing the incident rays. Exercises Q3. B, page 186. Answer the following question in detail. Define and describe the magnifying power of an optical instrument. Solution. Angular magnification or magnifying power of an optical instrument is defined as the ratio of the visual angle made by the image formed by that optical instrument beta to the visual angle subtended by the object when kept at the least distance of distinct vision alpha. Exercises Q3. B, page 186. Answer the following question in detail. Derive an expression for the magnifying power of a simple microscope. Obtain its minimum and maximum values in terms of its focal length. Solution. 1. Figure 8 shows the visual angle alpha made by an object when kept at the least distance of distinct vision d equals 25 centimeters. Without an optical instrument, this is the greatest possible visual angle as we cannot get the object closer than this. A. Visual angle alpha. B. Visual angle beta 2. Figure B shows a convex lens forming an erect, virtual, and magnified image of the same object when placed within the focus. 3. The visual angle beta of the object and the image, in this case, is the same. However, this time the viewer is looking at the image which is not closer than D. Hence the same object is now at a distance smaller than D. Exercises Q3. X page 186. Answer the following question in detail. Derive the expressions for the magnifying power and the length of a compound microscope using two convex lenses. Solution. 1. The final image formed in compound microscope A, B, as shown in the figure, makes a visual angle beta at the eye. 2. The visual angle made by the object from distance D is alpha. Compound microscope. Exercises Q3. X page 186. Answer the following question in detail. What is a terrestrial telescope and an astronomical telescope? Solution I. Telescopes used to see the objects on the Earth, like mountains, trees, players playing a match in a stadium, etc. are called terrestrial telescopes. E. In such a case, the final image must be erect. The eye lens used for this purpose must be concave, and such a telescope is popularly called a binocular. E. Most of the binoculars use three convex lenses with proper separation. The image formed by the second lens is inverted with respect to the object. The third lens again inverts this image and makes the final image erect with respect to the object. IV. An astronomical telescope is the telescope used to see objects like planets, stars, galaxies, etc. In this case, there is no necessity for an erect image. Such telescopes use a convex lens as an eye lens. Exercises Q3. She page 186. Answer the following question in detail. Obtain the expressions for magnifying power and the length of an astronomical telescope under normal adjustments. Solution. 1. For telescopes, alpha is the visual angle of the object from its own position, which is practically at infinity. 2. The visual angle of the final image is beta and its position can be adjusted to be at D. However, under normal adjustments, the final image is also at infinity, making a greater visual angle than that of the object. Telescope. 3. The parallax at the cross wires can be avoided by using the telescopes in normal adjustments. 4. The objective of focal length Φ focuses the parallel incident beam at a distance from the objective, giving an inverted image AB. 5. For normal adjustment, the intermediate image AB forms at the focus of the eye lens. Rays refracted beyond the eye lens form a parallel beam inclined at an angle beta with the principal axis. Exercises Q3. She I page 186. Answer the following question in detail. What is the limitation in increasing the magnifying powers of a simple microscope? Solution. Thus, the limitation in increasing the magnifying power is determined by the value of focal length and the closeness with which the lens can be held near the eye. Exercises Q3. Sheet E page 186. Answer the following question in detail. What is the limitation in increasing the magnifying powers of a compound microscope? Solution. Thus, in order to increase μ, we need to decrease UO. Thereby, the object comes closer and closer to the focus of the objective. This increases Vo and hence the length of the microscope. Therefore, μ can be increased only within the limitation of the length of the microscope. Exercises Q3. Sheet E page 186. Answer the following question in detail. What is the limitation in increasing the magnifying powers of the astronomical telescope? Solution. Thus, the magnifying power of the telescope can be increased only within the limitations of the length of the telescope. Exercises Q4. I page 186. Solve numerical example. A monochromatic ray of light strike the water n equals 4/3 surface in a cylindrical vessel at angle of incidence 53 degrees. Depth of water is 36 centimeters. After striking the water surface, how long will the light take to reach the bottom of the vessel? Angles of the most popular Pythagorean triangle of sides in the ratio 3, 4, 5 are nearly 37 degrees, 53 degrees, and 90 degrees. Solution. From figure, ray PO equals incident ray OA equals refracted ray QOB equals normal to the water surface. Given that angle POQ equals angle of incidence theta 1 equals 53 degrees. Exercises Q4. Page 186. Solve numerical example. Estimate the number of images produced if a tiny object is kept in between two plane mirrors inclined at 35 degrees, 36 degrees, 40 degrees and 45 degrees. Solution. The number of images seen when mirrors are inclined at 35 degrees, 36 degrees, 40 degrees, 45 degrees are 10, 9, 8 or 9, 7 respectively. Exercises Q4. Page 186. Solve numerical example. A rectangular sheet of length 30 cm and breadth 3 cm is kept on the principal axis of a concave mirror of focal length 30 cm. Draw the image formed by the mirror on the same diagram, as far as possible on scale. Solution. Exercises Q4. IV page 186. Solve numerical example. A car uses a convex mirror of curvature 1.2 meters as its rearview mirror. A minibus of cross-section 2.2 meters times 2.2 meters is 6.6 meters away from the mirror. Estimate the image size. Solution. Given that a minibus, approximately the shape of square, is at distance of 6.6 meters from the mirror, i.e., U equals 6.6 meters, i.e., H2 approximately equals 0.2 meters. Hence, the size of the image of minibus is nearly a square of edge 0.2 meters. Exercises Q4. V page 187. Solve numerical example. A glass slab of thickness 2.5 centimeters having refractive index 5/3 is kept on an ink spot. A transparent beaker of very thin bottom, containing water of refractive index 4/3 up to 8 centimeters, is kept on the glass block. Calculate apparent depth of the ink spot when seen from the outside air. Solution. When observed from the outside air, the light coming from the ink spot gets refracted twice, once through the glass and once through the water. Therefore, when observed from water, apparent depth equals 2 centimeters. Now when observed from outside air, the total real depth of ink spot can be taken as 8 plus 2 cm equals 10 centimeters. Exercises Q4. V page 187. Solve numerical example. A convex lens held some distance above a 6 cm long pencil produces its image of some size. On shifting the lens by a distance equal to its focal length, it again produces the image of the same size as earlier. Determine the image size. Solution. For a convex lens, it is given that the image size remains unchanged after shifting the lens through a distance equal to its focal length. From given conditions, it can be inferred that the object distance should be U equals F2. Exercises Q4. V page 187. Solve numerical example. Figure below shows the section ABCD of a transparent slab. There is a tiny green LED light source at the bottom left corner B. A certain ray of light from B suffers total internal reflection at nearest point P on the surface AD and strikes the surface CD at point Q. Determine refractive index of the material of the slab and distance dq. At Q, the ray PQ will suffer partial or total internal reflection. Angles of the most popular Pythagorean triangle of sides in the ratio 3, 4, 5 are nearly 37 degrees, 53 degrees, and 90 degrees. Solution. As the light ray undergoes total internal reflection at P, the ray BP may be incident at a critical angle. For a Pythagorean triangle with sides in ratio 3, 4, 5, the angle opposite to side 3 units is 37 degrees and that opposite to 4 units is 53 degrees. Exercises Q4. V page 187. Solve numerical example. A point object is kept 10 centimeters away from one of the surfaces of a thick double convex lens of refractive index 1.5 and radii of curvature 10 centimeters and 8 centimeters. Central thickness of the lens is 2 centimeters. Determine location of the final image considering paraxial rays only. Solution: given that R1 equals 10 cm, R2 equals 8 cm, U equals 10 cm and N equals 1.5. Exercises Q4. X page 187. Solve numerical example. A monochromatic ray of light is incident at 37 degrees on an equilateral prism of refractive index 3/2. Determine angle of emergence and angle of deviation. If angle of prism is adjustable, what should its value be for emergent rays to be just possible for the same angle of incidence? Solution: equals 65 degrees 27 feet I. Angle of emergence and angle of deviation in first case are 63 degrees and 40 degrees respectively. E. For emergent ray to just emerge with same incident angle, the angle of prism should have the value of 65 degrees 27. Q4. X page 187. Solve numerical example. From the given data set, determine angular dispersion by the prism and dispersive power of its material for extreme colors. NR equals 1.62 nanovolts equals 1.66, delta R equals 3.1 degrees. Solution. Exercises Q4. Sheet page 187. Solve numerical example. Refractive index of a flint glass varies from 1.60 to 1.66 for visible range. Radii of curvature of a thin convex lens are 10 cm and 15 cm. Calculate the chromatic aberration between extreme colors. Solution. Exercises Q4. Sheet page 187. Solve numerical example. A person uses spectacles of number 2.00 for reading. Determine the range of magnifying power, angular magnification possible. It is a concavo-convex lens, n equals 10.5, having a curvature of one of its surfaces to be 10 cm. Estimate that of the other. Solution. For a single concavo-convex lens, the magnifying power will be the same as that for a simple microscope, as the number represents the power of the lens. The
Making